All right, for basically all of modern physics, we've had this one core assumption, space-time. It's the stage, the backdrop, the container for everything that happens in the universe. But what if that's all wrong? What if we've had it completely backward? I mean, what if space and time aren't the stage at all, but just a shadow? A shadow cast by something much, much deeper. And that right there, that's the central, really mind-bending question we're going to tackle. The idea that space and time aren't fundamental building blocks, but instead they emerge from something else. We're going to dive into a pretty radical new idea. It's called dynamic vacuum field theory, or DVFT for short, and see how it completely flips our most basic ideas about reality on their head. Okay, so before we can build up this new idea, we've got to start by knocking down the old one. We have to look at the cracks in the foundation of space-time. So why is the idea of a fundamental space-time even a problem? Well, it's because we ask it to do all this physical stuff, right? We say it bends, it ripples with gravitational waves, it tells matter how to move. But think about it. A simple geometric grid, it's just lines on a graph. It has no physical substance. It can't actually do anything. I mean, just look at this, a coordinate grid. It's just imaginary lines, right? It's a map. It has no real substance. It can't push back when you accelerate, which is what inertia is all about. It can't ripple to carry gravitational waves across the cosmos. It can't store energy. It's just a description. A map isn't the territory, and it can't tell the territory what to do. But we know for a fact all these things do happen, so something's missing. And that's the whole point, isn't it? If the map isn't doing the heavy lifting, there has to be a real physical territory underneath it all. Something with actual tangible properties that can do the work. And this theory, DVFT, proposes that this something is a dynamic vacuum field. All right, let's get to the good stuff. Let's build this new foundation from the ground up. And to do that, we have to throw out everything we're used to. Forget points, forget coordinates, forget clocks. We're starting with just one single physical field. A field that exists before space and time even have a chance to show up. Now, you're going to see an equation here, but don't worry, we're not doing a math lecture. The key idea is incredibly simple. This field, called phi, isn't floating around in space. No, it is the medium that space itself is made from. It generates space. And the wildest part? It's made of just two fundamental ingredients. Yep, that's it. Everything, the whole universe, apparently emerges from just these two things. You've got the amplitude, rho, which you can think of as the thickness or the substance of this vacuum field, its density. And then you have the phase, theta, which is like the rhythm or the pattern running through that substance. It's what gives everything order and causality. So thickness and rhythm. That's the entire toolkit for building a universe. Kind of wild, right? Okay, so if all we have to work with is amplitude and phase, this thickness and rhythm, how in the world do we get back to something we recognize, like space and time? Well, this is where the theory gets really, really elegant. Let's start with space. How do you build space from scratch? The logic is just, it's so clean. Imagine two spots in this field. If their phase, their rhythm, is perfectly identical, then there's no separation between them. They are effectively in the same place. But the second their phase starts to differ, even a little bit, boom, you've created separation. And the amount of that difference in phase, that's what we perceive as distance. So here's the big takeaway. Space isn't some pre-existing box that everything sits inside of. It's just an expression, a description of all the different phase relationships happening in this fundamental field. So that's space. But what about time? You guessed it, time gets the same radical treatment. There's no giant cosmic clock ticking away for everyone. Nope. Time is simply a local measurement of how fast the vacuum's phase is evolving or changing. If that phase is evolving really fast in one spot, time moves quickly there. If it slows down, say near a massive object, time dilates. And if that phase evolution stops completely, well, time itself stops. Okay, cool. So this model can build space and time from scratch. That's impressive. But can it actually explain the forces of nature? What about the big one, gravity? Well, in this picture, gravity isn't a force that pulls you down. It's an emergent effect of the vacuum's properties changing from place to place. You know how a straw looks bent in a glass of water? That's refraction. Light bends when it moves from a thin medium, like air, to a dense one, like water. This theory says gravity is exactly the same thing. A massive object, like our sun, is just a region where the vacuum field is denser. It has a higher amplitude. And just like light bending in water, phase waves bend as they travel through this denser patch of vacuum. We experience that bent path as the force of gravity.
And this leads us to maybe the most famous number in all of science, c, the speed of light. In this theory, c isn't some magical fundamental rule of the universe. It's just a property of the medium it's traveling through, the vacuum. Think of it like the speed of sound. The speed of sound depends on the properties of the air, right? Its density, pressure, and so on. Well, the speed of light is the same. It's derived from the vacuum's stiffness and its density. The only reason the speed of light is constant is because the properties of the vacuum are constant everywhere.
So, the real test for any new theory isn't just what it explains, but what old problems it can solve. So let's throw two of the biggest mysteries in all of cosmology at it, black holes, and the very beginning of the universe itself. In this standard picture, what's at the heart of a black hole? A singularity, a point of infinite density where all the laws of physics just break. It's a huge problem, but DVFT has a much more elegant answer. A black hole is just a place where the vacuum gets so incredibly dense that the phase evolution, which, remember, is time, it just grinds to a complete stop. Physics doesn't break down, it just pauses. And the Big Bang gets a huge makeover, too. We tend to think of it as an explosion happening in space, but that can't be right, because space didn't exist yet. This theory suggests that before the beginning, the universe was in a state of perfect phase coherence, a totally silent, timeless, spaceless unity. The Big Bang wasn't an explosion. It was the moment that perfect, boring symmetry spontaneously broke. The phase started to decohere, differences popped into existence, and in that one instant, space, distance, and time were all born. So let's step back. What does all of this mean? We've essentially taken apart our most basic concepts, space and time, and rebuilt them from something much more fundamental. And in doing so, this perspective completely reframes our entire picture of reality. And if there's one sentence to take away from all this, it's this one. Spacetime, the world we see and experience, with all its beautiful rules and its gravitational curvature, it's just a shadow. It's the large-scale, macroscopic shadow cast by the incredibly simple dance of phase and amplitude happening on a level of reality we can't even begin to see. This really sums up the whole paradigm shift. Almost every other theory in physics starts by assuming spacetime is fundamental. They take the stage for granted and then try to figure out the actors. DVFT flips that completely on its head. It starts with the physics first, a real physical field, and shows how the stage, the geometry, emerges from the actors. It's the difference between just accepting the rules of the game versus actually explaining where the rules of the game come from. So in the end, a theory like this offers a powerful and elegant potential answer for how our universe works. But what's fascinating is that it also takes us right up to the very edge of what science can do. It might explain the transition from a state of nothingness to the reality we see around us, but it can never answer the ultimate question, why? Why is there something rather than nothing? And that, well, that's a question that might just lie beyond any theory or equation we can ever write.